You've been recovering wrong. Not because you're lazy, not because you're getting old, but because the supplement industry sold you a story built for 22-year-olds chasing hypertrophy, and nobody ever stopped to ask what happens when the rules change. Which they do, completely, somewhere around your 40th birthday. Here's the question I want you to sit with. What if the reason your body isn't recovering the way it used to has nothing to do with the supplements you're taking, and everything to do with when, in what order, and against which biological backdrop you're taking them? Most people in their 40s, 50s, and 60s are stacking supplements the same way they did at 25. Same creatine, same protein powder, same magnesium before bed. And they wonder why the soreness lingers 3 days instead of 1, why sleep doesn't fix them anymore, why they push hard on Monday and still feel it on Thursday. They blame age, they accept it, they slow down. That's the wrong conclusion. And this video is going to show you exactly why. In part 1, we covered the cellular biology of recovery. What actually breaks down, what needs to be rebuilt, and why the inflammatory window that follows intense effort looks fundamentally different after 40. If you haven't seen part 1, it's worth watching after this. But everything you need to understand the protocol will be here. What we're doing in this video is building the stack, not a generic list of supplements with vague benefits. A sequenced, mechanism-driven recovery protocol designed specifically around the biology of an adult over 40, accounting for hormonal context, mitochondrial efficiency, anabolic resistance, and the one factor almost every online guide completely ignores: the timing architecture. Because here's what nobody tells you. Supplements are not variables you add. They are interventions in a biological sequence. And if you intervene at the wrong moment, even with the right compound, you can blunt the very adaptation you're trying to accelerate. Some of what you've been told is helpful might actually be slowing you down. That's not a marketing line. There's mechanistic evidence behind it, and we're going to get into it. All protocols on this channel are reviewed by a clinical pharmacist and researcher, and all scientific references and evidence used are in the description below. This isn't a wellness blog. This is applied science, translated for people who want to perform at the highest level for the longest possible time. Take a breath. Get comfortable. Because by the time this video ends, you will have a complete evidence-based recovery stack that accounts for your current biology, not the biology of someone half your age. But first, I need to ask you something. And I'm not going to answer it yet, because the answer only makes sense once you understand what's happening inside the cells that are trying to rebuild you right now. The question is this: what if the most important supplement in your recovery stack isn't something you take, but something you stop taking at precisely the right time? Sit with that. It's going to matter. Let's start with the architecture of the problem, because if you don't understand what recovery actually requires at a biological level, not just muscle repair in broad strokes, but the precise molecular sequence that has to unfold, then any supplement stack is just guessing with expensive ingredients. When you train, whether it's resistance work, high-intensity intervals, or sustained endurance effort, you're initiating a controlled cascade of damage and repair. Muscle fibers sustain microtears. Mitochondrial membranes are stressed. Reactive oxygen species accumulate. The cytoskeletal scaffolding that holds muscle architecture in place is temporarily destabilized. This is normal. This is the stimulus. The body reads this damage as a signal. Something needs to be rebuilt, and this time, built better. What coordinates that rebuilding process is a sequence of signaling events. The inflammatory phase comes first, and it's not your enemy. Interleukin-6, released by working muscle, acts as both a local inflammation signal and a systemic energy-sensing messenger. Tumor necrosis factor alpha, prostaglandins, and neutrophil recruitment create the acute inflammatory environment that clears cellular debris and lays the groundwork for repair. Without this phase, the repair phase cannot begin cleanly. After the inflammatory window, typically peaking within the first 6 to 12 hours post-effort, the anabolic phase follows. Satellite cells, which are muscle stem cells sitting dormant along the muscle fiber, are activated. They proliferate, differentiate, and fuse with damaged fibers. mTORC1, the master regulator of protein synthesis, is upregulated in response to mechanical load and amino acid availability. Insulin-like growth factor 1 acts locally to amplify this anabolic signal. Growth hormone pulses during deep sleep to support tissue remodeling. And the mitochondria, the energy infrastructure of the whole operation, begin replication to meet the higher metabolic demands of the repaired tissue. This is how it works at 22. Efficient, rapid, nearly automatic. Now here's what changes after 40. The problem isn't that any one of these steps stops working. It's that the transitions between them become slower, noisier, and more easily disrupted. The inflammatory phase tends to persist longer, a phenomenon researchers now describe as inflammaging, the chronic low-grade inflammatory state that accumulates with age and is driven by senescent cells, mitochondrial dysfunction, and altered cytokine profiles. When the inflammatory phase doesn't resolve cleanly, the anabolic phase starts before the debris is cleared, and the repair that follows is architecturally messier. Meanwhile, anabolic resistance has set in. This means that the mTORC1 response to amino acids, specifically leucine, the primary trigger, is blunted. You need more leucine to achieve the same anabolic signal. This isn't a minor adjustment. Studies show that older adults may need up to 50% more dietary leucine to achieve equivalent mTORC1 activation compared to younger adults. If your protein intake and timing haven't adapted to this reality, your anabolic phase is running at reduced capacity. And here's where it gets interesting. And a little uncomfortable. Growth hormone secretion declines with age. That much everyone knows. But what's less discussed is that it's not just the volume that declines. It's the pulsatility. Young physiology releases growth hormone in sharp, high-amplitude pulses during slow-wave sleep. Older physiology releases it in flatter, more fragmented patterns, which means the downstream signaling to IGF-1 production in the liver is also fragmented. The tissue remodeling signal arrives muffled. This is the baseline. This is the terrain you're working with. And it means the supplement stack that works for the 25-year-old at the gym is not just suboptimal for you. It's operating on a completely different set of biological assumptions. But here's the part most doctors have never explained to you, and the part that changes everything about how you approach what comes next. The reason your recovery isn't just slower isn't because these mechanisms are weaker. It's because the communication channels between them have become less precise. The molecules are still there. The machinery is still functional, but the timing signals, the molecular clocks that tell each phase when to begin and when to yield to the next, are increasingly out of sync. And that means the intervention isn't about forcing harder, it's about restoring the rhythm. Which brings us to something most recovery protocols never even mention, and almost no one over 40 has been told about. The macrophages are the pivot point. Everything that happens before their phenotypic shift, the neutrophil recruitment, the debris clearance, the initial cytokine signaling, is preparation for the moment when the tissue transitions from demolition to construction. And everything that happens after that shift, the local anabolic signaling, the connective tissue remodeling, the satellite cell activation, depends on whether the shift happens cleanly, at the right time, with the right molecular context. Let's be precise about what this shift involves, because it's a more sophisticated biological event than most people realize. The macrophages that infiltrate the damaged muscle in the early post-exercise period are predominantly of what immunologists classify as the M1 phenotype. These cells are pro-inflammatory. They secrete TNF-alpha, IL-1 beta, IL-6, and IL-12. They produce nitric oxide via inducible nitric oxide synthase. They generate reactive oxygen species. Their function in the recovery context is specific. They phagocytose cellular debris, the fragments of broken sarcomers, the damaged mitochondrial remnants, the denatured protein aggregates, and prepare the tissue matrix for the arrival of repair-oriented cells. Without functional M1 macrophages doing their job completely, the tissue cannot be rebuilt cleanly. The construction crew cannot lay a foundation on rubble. The transition from M1 to M2 macrophage phenotype is the molecular handoff between cleanup and construction. M2 macrophages produce an entirely different secretory profile, They release IL-10, an anti-inflammatory cytokine that dampens the local pro-inflammatory environment. They secrete TGF-beta, which drives collagen synthesis in fibroblasts and supports connective tissue remodeling. And critically, in a detail that most recovery literature completely overlooks, they produce local IGF-1 directly within the muscle tissue. This local IGF-1 produced by M2 macrophages has been shown in peer-reviewed research to be quantitatively significant in the early anabolic response to muscle damage. It is not the same as systemic IGF-1 circulating in the blood in response to hepatic production driven by growth hormone. It is a local paracrine signal, acting directly on the satellite cells and muscle fibers in the immediate vicinity of the injury site. This local IGF-1 pulse is a primary driver of satellite cell activation and the initiation of myofiber repair. Now here is the critical aging variable. This M1 to M2 macrophage transition is directly dependent on the concentration of specialized pro-resolving mediators in the local tissue environment. Resolvins, specifically resolvin D1, D2, and E1, bind to receptors on M1 macrophages and program their phenotypic shift toward M2. Protectin D1 and myrisins perform complementary functions. Without adequate SPM concentrations at the tissue level, the M1 to M2 transition is delayed. The M1 macrophages linger. The pro-inflammatory cytokine environment persists. And the local IGF-1 pulse that should be initiating satellite cell activation and myofiber repair is absent or severely attenuated. This is the mechanism behind the prolonged soreness and impaired recovery that characterizes aging biology. It is not mysterious. It is not metaphysical. It is a specific molecular failure at a specific cellular transition point, and it can be directly addressed through targeted nutritional intervention. But there's a receptor story here that adds another layer of precision. The SPMs that drive this macrophage transition are produced from EPA and DHA through enzymatic pathways that are themselves regulated by a molecular system you've likely heard of, the cyclooxygenase and lipoxygenase pathways. COX2 specifically plays a dual role here that most discussions of anti-inflammatory supplementation miss entirely. COX2 is responsible not just for the prostaglandin synthesis that drives the pro-inflammatory response, but also, through aspirin-triggered lipoxin pathways, for the synthesis of 15-epi-lipoxin A4, which is itself a potent initiator of inflammation resolution. When you suppress COX2 with an NSAID, ibuprofen, naproxen, aspirin at anti-inflammatory doses, you blunt the prostaglandins, yes, but you also impair this resolution pathway. You don't just turn down the volume on inflammation. You selectively silence one of the voices telling the macrophages to shift. This is the mechanistic basis for why NSAIDs taken post-exercise have been shown in multiple clinical studies to impair long-term muscle adaptation. It's not just that they reduce inflammation. It's that they disrupt the resolution signaling that is supposed to succeed the inflammation. They interrupt the program at the transition point. And here's where the antioxidant story from the hook begins to connect. Because the same principle applies to high-dose exogenous antioxidants taken immediately post-exercise. The reactive oxygen species produced during and immediately after training are not random damage. They are signaling molecules. They activate NRF2, the master transcription factor for endogenous antioxidant defense. They activate NF-κB in specific patterns that coordinate the early inflammatory response. And critically, they activate AMPK, AMP-activated protein kinase, which is the primary cellular energy sensor that initiates the cascade leading to PGC1 alpha upregulation and mitochondrial biogenesis. If you flood the system with exogenous antioxidants, vitamin C, vitamin E, N-acetylcysteine, in the immediate post-exercise window, you quench these ROS signals. The NRF2 activation is blunted. The AMPK-PGC1 alpha axis is weakened. The mitochondrial biogenesis response, the reason your mitochondrial network should be expanding and upgrading after every hard session, is impaired. Multiple controlled studies, including the widely cited Ristow et al. Trial published in the Proceedings of the National Academy of Sciences, have demonstrated that high-dose antioxidant supplementation taken around exercise significantly reduces the metabolic adaptations to training, including insulin sensitivity and mitochondrial enzyme activity, in human subjects. The supplement you were most confident about may have been, in the window you were most confidently taking it, specifically counterproductive to the adaptation you were training to achieve. That's the uncomfortable truth at the center of window 1. But the story doesn't end with antioxidants and macrophage transitions, because beneath the immune system layer of recovery, beneath the SPMs, beneath the M2 shift, beneath the local IGF-1 pulse, there is an energetic infrastructure story that determines whether the repair that the macrophages have initiated can actually be executed. And that story takes place in the mitochondria. And what's happening inside those mitochondria after 40, the specific dysfunction, the specific feedback loop, and the specific reason it compounds with each training cycle, is the layer that explains why some adults over 40 feel like they never fully recover between sessions, no matter what they do. Recovery is not just a structural problem. It is not just about replacing damaged proteins and repairing torn sarcomeres. Recovery is, at its most fundamental level, an energetic problem. Every molecular event in the post-exercise repair cascade, satellite cell proliferation, ribosomal protein synthesis, chaperone-mediated protein refolding, collagen synthesis in fibroblasts, M2 macrophage recruitment and function, endoplasmic reticulum stress response. Every single one of these processes requires ATP. Sustained, reliable, high-fidelity ATP production, maintained at elevated levels for 24 to 72 hours after the training session has ended. And the structure responsible for producing that ATP, the mitochondrion, is itself damaged by the training session that initiated the repair cascade. The same exercise bout that triggers the need for recovery also directly stresses the mitochondrial network. Reactive oxygen species generated during intense exercise attack the mitochondrial inner membrane. The electron transport chain complexes, particularly complex Y and complex 3, are subject to oxidative modification. Mitochondrial DNA, which is circular and lacks the protective histones of nuclear DNA, is particularly vulnerable to oxidative damage and can accumulate mutations over time. And the mechanical stress of intense muscular contraction directly deforms mitochondrial membranes, disrupting the electrochemical gradient that drives ATP synthase. In a young, metabolically healthy adult, this mitochondrial stress is met by a rapid and robust quality control response. The damaged mitochondria are selectively identified and cleared through a process called mitophagy. The autophagy-mediated degradation of mitochondria that have lost sufficient membrane potential or are producing excessive ROS. The molecular machinery of this process centers on PINK1, P10-induced kinase 1, and parkin, an E3 ubiquitin ligase. When a mitochondrion is damaged and its membrane potential falls, PINK1 accumulates on the outer mitochondrial membrane, recruits parkin, and together they ubiquitinate the surface proteins of the mitochondrion, tagging it for autophagic degradation. The autophagic machinery wraps it in a double membrane vesicle, the autophagosome, and delivers it to the lysosome for breakdown and recycling. This is quality control. The damaged units are removed. The mitochondrial network that remains is leaner, more efficient, producing clean ATP with minimal ROS spillage. And the cleared-out mitochondria are replaced through biogenesis, the AMPK-PGC1 alpha axis, activated in part by the ROS and AMPK signaling from the exercise bout itself, drives the transcription of nuclear-encoded mitochondrial proteins, the replication of mitochondrial DNA, and the assembly of new mitochondrial units. The network expands. It improves. This is why endurance training improves mitochondrial density and aerobic capacity over time. After 40, this elegant quality control system begins to fail. And the failure is not in a single component. It's a systems-level degradation that compounds over time. First, PINK1 and parkin activity decline with age. The tagging and clearance of damaged mitochondria becomes less efficient. Mitochondria that have lost membrane potential and are generating excess ROS are not being cleared at the rate they should be. They accumulate. the proportion of dysfunctional mitochondria in the network increases. Second, lysosomal function, which is required for the final degradation step of mitophagy, declines with age. Lysosomes accumulate oxidized lipids and undegradable proteins, their pH becomes less acidic, and their hydrolase activity decreases. The autophagosomes containing the tagged mitochondria cannot complete their degradation efficiently. The entire mitophagy pipeline slows. Third, and most consequential for the feedback dynamics we're about to describe, the accumulation of dysfunctional mitochondria in the network is not passive. These damaged mitochondria continue to produce ATP, but at reduced efficiency and with substantially elevated ROS output. The electron transport chain in a mitochondrion with modified complex I or complex A3 leaks electrons. Instead of efficiently transferring them down the chain to ultimately reduce oxygen to water, electrons escape and react with oxygen to form superoxide. This superoxide is rapidly converted to hydrogen peroxide, which diffuses freely across membranes and acts as a signaling molecule. But in this context, an aberrant one. The elevated mitochondrial ROS feeds into the NLRP3 inflammasome, one of the central mechanisms of age-related chronic inflammation. The NLRP3 inflammasome, when activated by mitochondrial ROS, produces IL-1 beta and IL-18, two of the most potent pro-inflammatory cytokines in the human immune repertoire. This is the bridge between mitochondrial dysfunction and the inflammaging state we discussed in Block 2. Dysfunctional mitochondria are not just bad at making ATP. They are active drivers of the chronic low-grade inflammation that impairs post-exercise inflammatory resolution, delays the M2 macrophage transition, and reduces the local IGF-1 availability in recovering tissue. The loop closes on itself. Exercise stresses mitochondria. Mitophagy fails to clear the damaged units. The damaged units produce excess ROS. The ROS activates NLRP3. NLRP3 drives chronic inflammation. Chronic inflammation delays the post-exercise inflammatory resolution. The delayed resolution impairs the anabolic phase. And the next training session begins on a foundation of accumulated residual damage and chronic inflammatory noise. This is the loop. This is what you feel on day 2 and day 3, after a hard session when the fatigue hasn't cleared. This is what you're dealing with when you sleep 8 hours and still wake up feeling like you haven't recovered. The loop is running. The clinical data confirms this pattern with uncomfortable precision. Research published in the Journal of Physiology examining skeletal muscle biopsies in adults over 45 versus adults under 30, taken 48 hours after matched high-intensity exercise protocols, found significantly elevated markers of mitochondrial dysfunction, reduced mitochondrial membrane potential, elevated mitochondrial hydrogen peroxide production, and reduced activity of electron transport chain complexes in the older cohort. The younger cohort had substantially normalized these markers by the 48-hour mark. The older cohort had not. Separate data from the Buck Institute for Research on Aging has shown that NLRP3 inflammasome activation is directly upstream of the impaired inflammatory resolution we discussed in Block 3, creating a mechanistic link from mitochondrial quality to macrophage behavior that is both precise and actionable. Fix the mitochondria, and you partially fix the inflammation. Restore mitophagy efficiency, and you partially restore the M2 transition. You've felt this loop. You've blamed it on age, on volume, on inadequate sleep. Those are not the wrong answers, but they are incomplete answers. Because the intervention that breaks the loop is not sleeping more or training less. It is addressing the mitochondrial quality control failure and the NAD+ depletion that sits upstream of it. Now you understand the mechanism, but understanding is only half the equation, and this is where I want to be direct with you. The second half is what to do about it. And the approach most people take, adding more antioxidants, increasing recovery supplements, dosing everything higher, is precisely backwards. Almost everyone gets this wrong. And the reason they get it wrong is that they're treating the symptom without respecting the sequence. The sequence is everything. And before we get to it, there is one more layer, the deepest one, that connects the mitochondrial story to the peptide and epigenetic tools that make this protocol genuinely different from anything you've read before. We've traced the failure cascade from its most visible expression, slow recovery, persistent soreness, accumulated fatigue, down through the macrophage transition failure, and into the mitochondrial quality control dysfunction that drives it. Now we go one level deeper, into the molecular infrastructure that governs mitochondrial function, epigenetic regulation, and the peptide biology that can intervene in this cascade in ways that no conventional supplement even attempts. This is the layer that distinguishes what we do on this channel from the generic health content you can find anywhere online. We're not going to talk about magnesium in general terms. We're not going to say BPC 157 helps with recovery. We're going to trace the specific molecular mechanisms by which these compounds interact with the biological failures we've documented. And in doing so, we're going to show you exactly why the sequencing of the stack matters as much as the composition. Let's begin with NAD+, nicotinamide adenine dinucleotide, because it sits at the intersection of every failure we've discussed. NAD+ is a coenzyme present in every cell of the body. It participates in over 500 enzymatic reactions. In the mitochondria, it is the primary electron carrier in the electron transport chain, the molecule that shuttles electrons from the citric acid cycle to complex Y, enabling the proton pumping that drives ATP synthase. Without adequate NAD+, the electron transport chain slows. ATP production becomes inefficient. The energetic underpinning of the entire recovery cascade is throttled. But NAD+ role extends far beyond electron transport. It is the obligate substrate for a class of enzymes called sirtuins, NAD+ dependent deacylases that regulate gene expression, metabolic function, and stress response through post-translational modification of target proteins. 7 sirtuins exist in humans. For our purposes, 3 are essential. SERT1 deacetylates PGC1-alpha, the master transcriptional coactivator of mitochondrial biogenesis, activating it and initiating the transcription of nuclear-encoded mitochondrial proteins. When NAD+ is depleted, SERT1 is substrate-starved. PGC1-alpha remains in its acetylated, relatively inactive state. Mitochondrial biogenesis is suppressed. The damaged mitochondria that mitophagy failed to clear are not being replaced with new, functional units. The network degrades. SIRT3, which is located exclusively in the mitochondrial matrix, deacetylates and activates critical components of the electron transport chain, including key subunits of complexes Y, S2, and the 3. It also deacetylates and activates manganese superoxide dismutase, or SOD2, the primary mitochondrial antioxidant enzyme. When SIRT3 is active, the mitochondrial ROS load is managed by the cell's own endogenous antioxidant system. When SIRT3 is substrate-limited due to NAD+ depletion, SOD2 sits underactivated, ROS accumulates, and the NLRP3 inflammasome activation loop we described in Block 4 runs without meaningful internal opposition. SIRT6 operates in the nucleus, where it maintains telomere integrity, regulates DNA repair, and suppresses the expression of pro-inflammatory genes including TNF-alpha and IL-6. SIRT6 activity is directly linked to NAD+ bioavailability, and its decline with age contributes directly to the inflammaging phenotype that pollutes the recovery cascade. Now here is the critical epidemiological reality. NAD+ levels decline with age by approximately 50% between the ages of 40 and 60. This decline is driven by multiple factors. Increased activity of NAD+ consuming enzymes including PARP enzymes activated by oxidative DNA damage, and CD38, which is an NAD+ consuming enzyme whose activity increases dramatically with age and inflammation. The NAD+ deficiency is both a cause and a consequence of the dysfunction we've been describing. Oxidative stress depletes NAD+ by activating PARP, and NAD+ depletion impairs the SIRT3-mediated antioxidant defense that would otherwise suppress that oxidative stress. This is the epigenetic feedback loop that compounds with each decade, and each year of training without adequate mitochondrial support. Now let's bring in the peptide layer, specifically BPC 157, body protection compound 157. BPC 157 is a pentadecapeptide, a sequence of 15 amino acids that is partial derivative of a body protection compound isolated from human gastric juice. It has been studied in over 70 published studies in rodent models, with growing practitioner data and case report evidence in humans. Its mechanisms are diverse, but in the context of post-exercise recovery in adults over 40, three are specifically relevant. First, BPC-157 upregulates endothelial nitric oxide synthase, or eNOS, the enzyme responsible for nitric oxide production in the vascular endothelium. Nitric oxide mediates vasodilation, increasing blood flow to recovering tissue. But its significance in the recovery context extends beyond hemodynamics. Nitric oxide is a signaling molecule that participates in satellite cell activation, mitochondrial biogenesis, and the regulation of the inflammatory phenotype of macrophages. In aging vasculature, eNOS activity is reduced, partially explaining the impaired nutrient and oxygen delivery to recovering tissue that compounds the energetic failure in the mitochondrial network. Second, BPC-157 has been shown to upregulate growth hormone receptor expression in tendon fibroblasts, and, by extrapolation from mechanistic studies, in other connective tissue compartments. This is a receptor sensitization effect, in a physiology where circulating growth hormone has declined and the downstream IGF-1 signal is weakened. BPC-157 makes the available signal more effective. It doesn't increase GH production. It increases the tissue's capacity to respond to the GH that is present. Third, and perhaps most relevant to the macrophage story in Block 3, BPC-157 activates the VEGFR2 pathway, the primary driver of angiogenesis, and promotes the vascularization of healing tissue. This angiogenic response is not merely about blood supply. It is the structural requirement for M2 macrophage recruitment into the repair zone. M2 macrophages, the anti-inflammatory, pro-repair phenotype that produces local IGF-1 and TGF-beta, are recruited from the circulation. Their arrival at the repair site requires functional vasculature into and through the healing tissue. BPC-157, by supporting angiogenesis in the recovery window, creates the vascular infrastructure through which the resolution phase can complete. This is not a supplement blunting your inflammation. This is a peptide supporting the specific biological transition that aging biology fails to complete efficiently. The mechanism is precise, the target is specific, and the intervention window, as we will detail in Block 8, is critical. The third layer of this deepest block is a newer conversation in the longevity and recovery space. The role of senolytics and xenomorphics in clearing the background noise that impairs every recovery cycle. Cellular senescence, the accumulation of cells that have exited the cell cycle but resist apoptosis and secrete a pro-inflammatory cocktail of cytokines, chemokines, and proteases known as the senescence-associated secretory phenotype, or SASP, is now recognized as a primary driver of inflammaging. Senescent cells accumulate in muscle tissue, connective tissue, and the vasculature with age. Their SASP feeds the chronic inflammatory state that contaminates the post-exercise recovery cascade. Compounds that selectively eliminate senescent cells, quercetin and dasatinib in the clinical senolytic literature, or that suppress the SASP without eliminating the cells, compounds like fisetin and navitoclax in more recent research, represent a frontier of recovery optimization that is only beginning to be integrated into practical protocols. We're not going to incorporate the full senolytic discussion into today's protocol. It deserves its own dedicated video, and it's coming. But the mechanistic connection is important. Addressing the senescent cell burden is the upstream intervention that reduces the baseline inflammatory noise against which every post-exercise recovery cascade is trying to run. Everything we've covered, the SPM synthesis failure and macrophage transition delay, the mitochondrial dysfunction and mitophagy failure and NLRP3 activation, and now the NAD plus depletion, Sirtuin suppression, and senescent cell accumulation, all of this points toward a practical conclusion. It points toward a protocol that doesn't treat recovery as a single event to be addressed with a single post-workout shake, but as a multi-phase biological program to be supported with precision at each phase transition. That protocol is what comes next. And the way it's structured, the principles of timing and sequencing that organize every compound in the stack, is what makes it genuinely different from anything you've read before. Let's step back and look at the full picture together. Because what we've built across the last 4 blocks is not simply a collection of interesting biochemistry. It is a mechanistic architecture, a precise, interconnected model of why recovery fails in the aging body, where the specific failure points are, and how they interact to produce the experience you have lived through after every hard session that didn't resolve the way it was supposed to. The architecture has 3 layers, and they stack on each other. The first layer is the inflammatory resolution failure. The post-exercise inflammatory cascade, which is necessary, which is the signal, which cannot and should not be suppressed, is running in an aging biology that has lost the molecular infrastructure to resolve it cleanly. The specialized pro-resolving mediators, resolvins, protectins, myrcins, are being synthesized at insufficient rates because the enzymatic conversion of omega-3 precursors has become less efficient with age. Without adequate SPMs in the local tissue, the M1 to M2 macrophage transition is delayed. The macrophages that need to shift from debris clearance to active repair support don't receive the resolution signal on time. The local IGF-1 pulse that M2 macrophages would provide to the satellite cells and damaged fibers doesn't arrive. The anabolic phase starts late, in a contaminated environment, without the local growth factor support it requires. The second layer is the mitochondrial quality control failure. The mitochondria that need to power the entire repair cascade are themselves damaged by the training session that initiated the cascade. In young physiology, damaged mitochondria are rapidly cleared by mitophagy and replaced by biogenesis. In aging biology, PINK1 Parkin-mediated mitophagy is impaired, lysosomal function is reduced, and damaged mitochondria accumulate in the network. These dysfunctional units produce ATP at reduced efficiency and ROS at elevated rates. The elevated mitochondrial ROS activates the NLRP3 inflammasome, which produces IL-1 beta and IL-18, feeding back into the pro-inflammatory environment that is already struggling to resolve. The energy infrastructure of the repair cascade is compromised at exactly the moment it is most needed. The third layer is the NAD+ and Sirtuin failure, the epigenetic multiplier that compounds both of the previous failures simultaneously. NAD+ depletion suppresses Sirtuin, reducing PGC1 alpha activity and impairing mitochondrial biogenesis. It suppresses Sirtuin, reducing SOD2 activity and allowing mitochondrial ROS to accumulate. It suppresses Sirt6, reducing the cell's capacity to manage the pro-inflammatory gene expression that drives inflammaging. CD38 activity, which increases with age and inflammation, consumes NAD+ faster than the salvage pathway can restore it, creating a progressive depletion that deepens with each training cycle if not actively addressed. These 3 layers interact. The inflammatory resolution failure extends the pro-inflammatory window, which activates PARP enzymes through oxidative DNA damage, which depletes NAD+, which suppresses sirtuins, which impairs mitochondrial quality control, which increases mitochondrial ROS, which activates NLRP3, which extends the pro-inflammatory window further. It is a loop, self-reinforcing, directional, and progressive over time unless specifically interrupted. Now I want to give you an analogy that I think captures this precisely. And I want to offer it not to simplify the science, but to make the architecture viscerally clear in a way that serves the protocol logic. Imagine a city that has just experienced a controlled demolition, a necessary one, part of a planned reconstruction project. The demolition was deliberate. Debris fills the site. 3 things need to happen in sequence. The debris must be cleared, the power infrastructure must be restored, and the construction crew must be given clean working conditions and the materials they need. In a young, functional city, each service is dispatched precisely. The cleanup crew arrives, does their work, and leaves the site clean. The power utility restores electricity to the grid. The construction crew arrives into a cleared, powered, supplied environment and begins building. The process is efficient. The building is completed on schedule, and it's stronger than what was there before. In the aging city, which is your body after 40, the cleanup crew arrives but works slowly, and some of them don't leave when they're supposed to. They're still on site when the construction crew arrives, creating confusion and conflict. The power infrastructure is running on aging generators that are themselves in disrepair. They're producing power, but inconsistently, with brownouts, and the generators themselves are emitting exhaust that gets into the construction materials. The supply chain that should be delivering raw materials, local IGF-1, amino acids in the right quantities at the right time, the cofactors that enable enzymatic function, is fragmented and delayed. The construction crew is capable. The building plan is intact. But the site conditions are a mess. The power is unreliable, and the materials keep arriving out of sequence. The building gets finished, but it takes 3 times as long. It's not quite as structurally sound as it could have been. And the next demolition cycle is scheduled to begin before the last project has fully resolved. This is why you feel the way you do on day 3 after a hard session. This is the mechanism. And here is what the supplement stack is, when it's designed correctly. It's not a force multiplier. It's not about pushing harder through the recovery. It's a site management protocol. It provides the cleanup crew with the specific molecular tool that tells them when to hand off to construction. It restores the power infrastructure by providing the substrate the epigenetic generators need to run cleanly. And it ensures that the raw materials, the amino acids, the growth factor signals, the vascular access for M2 macrophage recruitment, arrive in the right place, at the right time, in the right sequence. The supplement stack, understood correctly, is a timing and coordination intervention. Not a volume intervention, not a suppression intervention, a coordination intervention. The sequence of what comes next, the detailed protocol, is more important than any single compound in it. Many adults over 40 have tried creatine. Many have tried omega-3s. Many have experimented with NMN. Very few have taken them in a sequence that respects the biological logic of the recovery cascade, in timing windows calibrated to the phase transitions we've described. With an understanding of what each compound is doing and when it should not be taken. The next 2 blocks will give you that sequence in complete detail. Specific compounds, specific dose ranges, specific timing windows. And for each recommendation, the mechanistic thread that ties it directly back to the architecture we've built in this video. Nothing arbitrary. Nothing included because it's popular. Every element is there because it targets a specific failure point in the recovery cascade, at the specific moment that failure point is most accessible to intervention. Get ready. Because what comes next is the most specific, most evidence-grounded, and most practically applicable recovery protocol designed specifically for an adult body over 40 that you have encountered anywhere. The protocol is built around 3 time windows. Not a single post-workout window, not a morning stack and an evening stack in the generic sense. 3 precisely defined biological windows, each corresponding to a distinct phase of the recovery cascade, each requiring a fundamentally different set of interventions based on what the cellular environment looks like during that phase and what the biology is trying to accomplish. This 3-window architecture is the single most important structural feature of the entire protocol. It is what separates a recovery stack that works from one that has all the right ingredients, but produces mediocre results. And once you understand why the windows exist, once you can trace the logic from mechanism to timing, you will never approach a post-workout supplement decision the same way again. Let's establish the windows clearly before we go through the specific compounds. Window 1 is the immediate post-exercise phase, extending from the end of your training session to approximately 2 hours after. During this window, the inflammatory cascade is in active recruitment phase. Neutrophil infiltration is ongoing or at its peak. The ROS produced by the working muscle is still elevated and actively serving as a signaling molecule, activating AMPK, stimulating NRF2, initiating the PGC1 alpha cascade that will drive mitochondrial biogenesis. IL-6 from the muscle is circulating. Satellite cells are receiving the initial mechanical and chemical activation signals. The governing principle for window 1 is support, do not suppress. The biological program is running. Your job is to provide the raw materials it needs, primarily protein and leucine to meet the mTORC1 activation threshold, creatine to support phosphocreatine resynthesis, and electrolytes to restore the osmotic environment for normal cell signaling, without introducing anything that interferes with the signaling that is actively directing the recovery cascade. High-dose antioxidants are specifically contraindicated in window 1. We've established the mechanism. Vitamin C, vitamin E, and N-acetylcysteine in pharmacological doses quench the ROS that is activating AMPK and PGC1-alpha, blunting the mitochondrial biogenesis response to training. This is not a minor nuance. The Ristow et al. Study showed that 1,000 millimers of vitamin C and 400 IU of vitamin E taken around exercise prevented the exercise-induced improvements in insulin sensitivity and the upregulation of key mitochondrial biogenesis markers in human subjects. High-dose curcumin has similar effects through its potent antioxidant and NF-κB suppression activity. NSAIDs, including ibuprofen commonly taken for muscle soreness, suppress COX-2 and impair the aspirin-triggered lipoxin pathway that initiates the resolution cascade, as well as impairing prostaglandin-mediated muscle protein synthesis. None of these belong in Window 1. Window 2 begins at approximately 2 to 6 hours post-exercise and extends through roughly the 8 to 10 hour mark. This is the transition window, the biological moment at which the body is moving from the inflammatory phase to the resolution phase. The neutrophil activity is winding down. Monocytes have been recruited from the circulation and are differentiating into macrophages within the tissue. The M1 macrophages are beginning to receive the SPM-mediated resolution signals that will drive their phenotypic shift. This is the most important window for targeted supplementation, and the one most consistently neglected in conventional recovery protocols. The compounds that belong here are those that support the SPM synthesis and M2 macrophage transition, specifically high-quality omega-3s in the triglyceride form, as well as the peptide interventions that support vascular access, GH receptor sensitization, and connective tissue remodeling. This is also the window for NAD+ precursors, which need adequate time to be processed through the biosynthetic pathway before their effects on Sirtuin activity become significant. Window 3 is the nocturnal recovery window, the period from approximately 2 hours before sleep through the sleep period itself. This is the window in which the majority of structural tissue remodeling occurs. Growth hormone is secreted in high-amplitude pulses during slow-wave sleep. IGF-1, both systemic and local, supports the ongoing proliferation and differentiation of satellite cells. The anabolic machinery that was activated in the previous windows is now executing against a background of greatly reduced metabolic activity in non-recovery tissues, allowing the body to allocate maximal energy and hormonal signal to the repair site. The compounds that belong in Window 3 are those that support sleep architecture and slow-wave sleep depth, suppress late-day cortisol dysregulation that fragments sleep onset, provide the amino acid substrates for overnight collagen synthesis, and create the endocrine environment that maximizes the nocturnal GH pulse. Before we go through the full details, I want to take a brief and genuine pause. This channel is approaching a meaningful milestone in its growth. If this content is reaching you, if these are the conversations about health and performance that you've been looking for and haven't found elsewhere, subscribing right now makes a real and direct difference. Everything here is reviewed by a clinical pharmacist and researcher. There are no products being pushed for commission, no affiliate angles, no compromises in the science, just rigorous, honest, applied work for adults who take their health and longevity seriously. If this is your kind of content, hit subscribe. It costs you nothing and ensures this work continues. Now, back into the protocol, because what comes next is the specific implementation of all 3 windows, and the compounds that build each one are going to arrive with their mechanisms already established from the blocks you've just worked through. There is also a principle of interaction effects that I want to flag before we go into the full detail. Because understanding how the compounds in this stack interact with each other across the windows is as important as understanding what each one does individually. NAD+ precursors taken in Window 2 create a substrate environment that makes the Sirtuin activators taken in Window 3 more effective. The omega-3s taken in Window 2 that support SPM synthesis also improve the cell membrane environment for BPC-157's receptor interactions. The glycine that supports collagen synthesis overnight also improves sleep architecture, which amplifies the GH pulse that enhances the sensitivity of GH receptors that BPC-157 has upregulated in the connective tissue. These are not coincidental interactions. They are cascading benefits, a designed synergy that is only available when the sequencing is correct. The sequence is more than the sum of the parts, and the complete sequence is the block that follows. Here is the full protocol, organized by window, with every recommendation tied directly to the mechanistic foundations established in this video. This is not a list of popular recovery supplements. This is a sequenced, evidence-grounded intervention map for the 3 critical windows of post-exercise recovery in an adult over 40. Window 1, 0-2 hours post-exercise, leucine-enriched protein, 40-50 grams total protein, targeting 3. 5-4, 0 grams of leucine. This is the non-negotiable foundation of Window 1. The anabolic resistance of aging skeletal muscle means that the mTORC1 activation threshold, the leucine concentration required to initiate a maximal muscle protein synthesis response, is significantly higher than in young muscle. Studies by Churchward Van Moore and colleagues have established that 40 grams of protein, with a leucine content at or above 3.5 grams, is required to produce a muscle protein synthesis response in older adults, equivalent to what 20 grams achieves in younger subjects. Whey protein isolate or concentrate is the optimal vehicle. It is rapidly digested, has the highest leucine content of any protein source at approximately 10–11% by weight, and produces a rapid, high-amplitude plasma amino acid appearance that matches the narrow timing window of peak mTORC1 sensitivity. If plant-based sources are used, pea dark rice blend, add 2–3 grams of free-form leucine to compensate for the lower leucine density of plant proteins. If you eat a large meal immediately post-training, rather than using a shake, ensure the protein source is high quality and leucine dense, and consider the meal timing relative to the window. The anabolic window is real in aging biology, even if it's sometimes overstated for younger adults. Creatine monohydrate, 3–5 grams. Creatine replenishes the phosphocreatine pool that was depleted during high-intensity work, restoring the rapid ATP resynthesis capacity of the muscle. In the recovery context, creatine has additional mechanisms. It has been shown to reduce the degree of exercise-induced muscle fiber damage, support satellite cell activity, and, through emerging mitochondrial research, assist in maintaining mitochondrial membrane potential in the acute post-exercise period, reducing the mitochondrial dysfunction that drives ROS accumulation and the NLRP3 loop. There is no superior timing for creatine relative to post-workout specifically. The research supports any consistent daily timing, but post-exercise with protein is practical and supported. Electrolyte replacement: sodium 500 1000 ml, potassium 300 500 ml, magnesium 150 200 ml in glycinate or malate form. The osmotic environment of the cell is not a background variable. It is an active regulatory context for virtually all the signaling events in Window 1. Sodium restores plasma osmolality and supports aldosterone signaling. Potassium is critical for membrane potential and normal Na+, K+ ATPase function. Magnesium in Window 1, particularly in the malate or glycinate form, which has higher bioavailability than oxide, serves as a cofactor in ATP synthesis, protein translation, and hundreds of enzymatic reactions that are running at elevated rates during the recovery initiation. Magnesium deficiency is prevalent in athletic populations and is directly associated with reduced muscle function and impaired recovery. What to actively avoid in Window 1: high-dose vitamin C, high-dose vitamin E, N-acetylcysteine at pharmacological doses, curcumin at anti-inflammatory doses, ibuprofen and other NSAIDs. The mechanistic basis for avoiding these in this window has been established in blocks 2, 3, and 5. They suppress the ROS, prostaglandin, and NF-κB signaling that are required for the recovery program to initiate correctly. Save your antioxidant and anti-inflammatory support for Window 2, where it can be used strategically rather than destructively. Window 2, 2–6 hours post-exercise. Omega-3 fatty acids, triglyceride form, 2–3 grams combined EPA and DHA. This is the most evidence-supported intervention for improving the quality of inflammatory resolution in aging biology. EPA and DHA are the direct biosynthetic precursors to resolvins, protectins, and maricins. the specialized pro-resolving mediators that drive M1 to M2 macrophage transition and enable the local IGF-1 pulse in recovering muscle. The triglyceride form has significantly higher bioavailability than the ethyl ester form found in most mass-market fish oil supplements. Look for labels that specify TG or reesterified triglyceride form, or use krill oil, which is naturally in phospholipid form with excellent absorption. Timing matters specifically here. Taking omega-3s in window 2 rather than with breakfast means they are circulating as substrates for SPM synthesis precisely when the macrophage transition is occurring. This is not a trivial timing consideration. It is mechanistically precise. BPC 157, 250, 500 mcg subcutaneous injection, or 500 mcg 1, Beamer oral sublingual. For sessions involving significant connective tissue load, tendons, ligaments, fascia, joint structures, BPC 157 in window 2 targets the specific mechanisms that support recovery in these tissues. It upregulates eNOS and nitric oxide availability for tissue perfusion. It sensitizes growth hormone receptors in fibroblasts, amplifying the tissue response to whatever GH signal is available. It drives VEGFR2-mediated angiogenesis into the repair zone, creating the vascular access required for M2 macrophage recruitment. The oral route has lower bioavailability, but is still biologically active through enteric absorption and systemic distribution. Subcutaneous injection, in jurisdictions where peptides are legally available and under appropriate medical guidance, provides more consistent systemic availability. This is a prescription compound in most regulated markets. Use it under appropriate medical supervision. NMN, 500 x 1000 milliliter, or NR, 300-600 milliliters. This is the NAD plus restoration intervention, addressing the epigenetic multiplier failure from Block 5. NMN enters the NAD plus biosynthetic pathway directly at the NMN stage, bypassing several enzymatic conversion steps. NR enters one step earlier. The downstream effects on NAD plus bioavailability, and through that, on Sirt1, Sirt3, and Sirt6 activity, on PGC1 alpha activation and mitochondrial biogenesis, on SOD2 activation and mitochondrial ROS management, and on the resumption of functional mitophagy through the Sirt1-mediated autophagy pathway. Make this intervention one of the highest leverage in the stack for an adult over 40. Effects are cumulative with consistent daily use. Acute timing in window 2 is supported by practitioner data. Emerging research suggests that the post-exercise metabolic state is an optimal context for NAD plus precursor utilization. Glycine, 5 to 10 grams. Glycine is the most abundant amino acid in collagen, specifically in the GlyXY repeat sequence that forms the triple helix of types 1 and the 3 collagen. Without adequate glycine availability, collagen synthesis is rate-limited regardless of the anabolic signal quality. In window 2, when the fibroblasts in connective tissue are receiving the TGF-beta and local IGF-1 signals that drive collagen remodeling, glycine availability is the substrate that determines how effectively they can execute. Glycine also functions as a precursor to glutathione, the body's primary endogenous antioxidant, which becomes important in the later recovery stages when controlled antioxidant support is appropriate. Additionally, glycine is a central nervous system inhibitory neurotransmitter that improves sleep quality and architecture, directly supporting the nocturnal GH pulse in window 3. Window 3. Evening, 2 to 3 hours before sleep, and during the nocturnal period, magnesium glycinate or threonate, 300-400 milliliters elemental magnesium. Magnesium glycinate provides the most bioavailable form of systemic magnesium with excellent gut tolerance. Magnesium threonate has superior blood-brain barrier penetration and preferentially elevates cerebrospinal magnesium concentrations, making it more effective for the CNS-mediated sleep architecture effects, specifically the enhancement of slow-wave sleep depth that is required for high-amplitude GH pulsatility. Either form is appropriate. The combination of both, 200 milliliters glycinate and 200 milliliters threonate, is used by practitioners seeking both systemic and CNS-targeted magnesium support. Take away from calcium supplementation if used. They compete for intestinal absorption through the same transport channels. Zinc picolinate or bisglycinate, 15 to 30 mg elemental zinc. Zinc is a cofactor for IGF-1 signaling at the receptor level, for testosterone biosynthesis in Leydig cells, and for the activity of over 300 metalloenzymes that participate in protein synthesis and cellular repair. Zinc status is depleted by intense training through sweat and urinary losses, and suboptimal zinc is a direct suppressor of anabolic hormonal signaling in aging males. The picolinate and bisglycinate chelated forms have superior absorption over zinc oxide or sulfate. Evening timing in window 3 aligns zinc availability with the nocturnal anabolic window and the period of peak hormonal synthesis. Phosphatidylserine. 400 mg phosphatidylserine, a phospholipid naturally abundant in neuronal membranes, has specific clinical evidence for suppressing exercise-induced cortisol elevation. In aging adults who train intensely, late-day cortisol levels can be chronically elevated, disrupting sleep onset, fragmenting sleep architecture, and directly suppressing GH pulsatility by antagonizing the GH-releasing hormone signal at the pituitary. A 400 mg dose taken in the pre-sleep period has been shown in multiple clinical trials, including studies by Monteleone et al., to significantly blunt the cortisol response to exercise and reduce the cortisol to DHEA ratio, restoring the hormonal context in which deep, GH-rich sleep can occur. L-theanine. 200-400 mg L-theanine, the amino acid primarily found in green tea, promotes alpha-wave brain activity and GABAergic tone without sedation. In the context of window 3, it supports the relaxed, drowsy without anxious state that facilitates natural sleep onset. It does not directly impact GH pulsatility, but reduces the nighttime cortisol and sympathetic nervous system activity that would otherwise fragment slow-wave sleep. GH-releasing peptides, per prescribing physician's protocol. For adults working with physicians who have initiated a GH optimization protocol, the pre-sleep window is the physiologically appropriate timing for GH-stimulating peptides. CJC-1295, combined with ipamorelin, creates a synergistic GH pulse. CJC-1295 acting on the GHRH receptor to extend the GH pulse, and ipamorelin acting on the ghrelin receptor to amplify the amplitude, mimicking the youthful high-amplitude nocturnal GH secretory pattern that drives tissue remodeling. This is a prescription protocol, not a self-directed supplement recommendation. It is included here because the mechanistic context established in this video, specifically the importance of GH pulsatility in the nocturnal recovery window, explains why this class of intervention is used and why the timing matters. All protocols on this channel are reviewed by a clinical and research pharmacist, because accuracy here is not optional. These compounds, these dose ranges, these timing windows are not assembled from wellness influencer content. They are derived from peer-reviewed literature, clinical pharmacology, and the specific mechanistic framework established in this video. Every reference is in the description below. Apply this protocol with the seriousness it deserves. And if you are managing any chronic conditions, taking prescription medications, or working with a physician on hormonal optimization, integrate these recommendations within that clinical context, not outside it. The complete stack is not meant to be implemented all at once, and it's not meant to be intimidating. Begin with the foundational layer, leucine-enriched protein in window 1, omega-3s in window 2, magnesium and zinc in window 3. Build for 2 to 4 weeks. Add creatine if you haven't already. Add glycine. Then introduce NMN or NR. Then, if connective tissue recovery is a priority and you have access to it through appropriate channels, consider BPC 157 for the sessions that challenge that tissue most. Build the stack the way biology builds a structure, in sequence, with patience, with each layer firmly established before the next one is added. Do you remember the question from the beginning of this video? What if the most important supplement in your recovery stack isn't something you take, but something you stop taking at precisely the right time? You know the answer now. And what I want you to notice is that it wasn't a trick question. It wasn't designed to be provocative or dramatic. It was a precise description of a real biological phenomenon, one that has likely been costing you adaptation, costing you recovery quality, and costing you training returns for years. The antioxidants you trusted, the anti-inflammatories you reached for. Not because they're bad supplements in isolation, but because at the moment you were taking them, in the window you were using them, they were silencing the very signals your body was sending to itself to initiate recovery. The transformation that was promised in the first 30 seconds of this video wasn't about the supplements themselves. It was about the shift in how you understand what your body is doing after every hard session, and what it actually needs from you, versus what it needs you to get out of the way of. You have a body that is still running every phase of the recovery program. The inflammatory cascade is still activating. The satellite cells are still waiting for their signal. The mitochondria are still trying to clear their damaged units and rebuild the network. The Sirtuins are still waiting for the NAD+ substrate that would let them do their jobs. The macrophages are still trying to make the transition from demolition to construction. The program is intact. It is simply running in a body whose molecular infrastructure has become less efficient, more sensitive to interference, and more dependent on precise contextual support than it was 20 years ago. That's not a limitation. That's information. That's a map. Every mechanism we traced in this video is a point of access. A place where a precisely timed, mechanistically grounded intervention can restore the efficiency of a phase transition that has been running below capacity. Every compound in the protocol is there because it sits at one of those access points, with a clear molecular rationale for why it helps when applied at the right time, and why it hurts when applied at the wrong one. The people who age well, who maintain functional capacity, physical performance, and metabolic health into their 60s, 70s, and beyond, are not the ones who found a secret supplement. They are the ones who stopped treating their biology as something to be overridden and started treating it as something to be understood, respected, and supported. They are the ones who asked not just what to take, but when, why, and in what order. They are the ones who recognize that the body after 40 is not a diminished version of the body at 22. It is a more complex one, requiring more nuanced inputs, rewarding greater precision with greater results. You now have the science. You have the architecture. You have the protocol. What you do in the 48 hours after your next hard session is where this video stops being information and starts being transformation. And the most powerful part of what you've just learned is this. You didn't need a new supplement. You needed a new framework. The compounds were always available. The mechanism was always there. What was missing was the map. You have the map now. If this video reached you in a meaningful way, I want to ask something simple. Think of 5 people in your life. Training partners, colleagues, family members, anyone over 40 who is pushing themselves physically and wondering why the recovery doesn't match the effort. Share this video with them, not as a recommendation, as a gift. Because what we've covered here isn't widely known, isn't being said loudly enough, and represents hours of work, clinical review, and mechanistic research that most people will never encounter in the usual places they look for health information. Leave a comment below. Tell us where you're starting with the protocol. Tell us which mechanism landed hardest for you. And if you have a question that this video raised but didn't fully answer, about a specific peptide, a specific mechanism, a specific symptom pattern you've been trying to understand, write it below. That's where the next video comes from. This channel is built one subscriber and one conversation at a time. If you haven't subscribed yet, now is the moment. And if you're already here, thank you for being part of this. The work continues.